So, meine sehr verehrten Damen und Herren, ich darf Sie herzlich begrüßen zu meinem Vortrag. Messieurs, dames et messieurs, welcome à mon présentation. I think I will switch to English because both German and French will not be much fun for you. So thanks a lot for inviting me to give this presentation. I tried to collect a few topics that I hope are of interest to you and are not already known to everybody. Otherwise, I can cite a famous person who said, some things are so important that you can hear them several times. Or as Christian once said when I apologized that he would sit in the same talk that I gave at another occasion, and he said, but it's no problem. It's like with a symphony. You can listen to it several times. Okay, so not that I want to compare my talks to a symphony, but let's get started. So I choose this very generic title when I was asked half a year ago what I would talk about. And then I realized that some years ago in this very same conference, there was a talk by my dear colleague Aline Bostan and Bruno Salvi, which had almost the same title, modulo synonyms of computer algebra and symbolic computation, algorithmic methods. And I checked, and I was afraid that, okay, now what should I do? This talk has already been given. So I looked at the contents. This is the contents of the talk. And yeah, so then to my relief, I realized that this is more or less disjoint to what I'm going to talk about. However, since this talk had been given at this conference, of course, I assume that all these topics are very well known to you, and I will base on this preliminary theory. Okay, so here is what I plan. Maybe it's very ambitious, so let's see how far we can get. So my plan is to have 4 blocks, 2 in each lecture. So that means today I'm going to talk about cylindrical algebraic decomposition and lattice reduction LLL. And each of these things I will somehow, I will not go too deep into theory how these things work, but more how they can be applied in combinatorics and other fields of mathematics. Yes, this is the intersection, so this is tomorrow. I said almost disjoint. Okay, so I will start with cylindrical algebraic decomposition, and there's a pun that actually I found out sadly only works in German. So you recognize what this is? Here is another picture. So this is what in German is called a cylinder. But neither in English it's called a cylinder, in English it's called a top hat, nor in French, I looked it up, it's called something like haut de forme. And so by the way, this right picture is a haut de forme that I found in my parents' house, and it must have belonged to my great-grandfather, we believe, we don't know, it was hidden in some very hidden corner. Okay, and so this is the connection to cylindrical algebraic decomposition, and this is a method that relies to quantifier elimination over the reals. So there's a classical result that is a so-called Tarski-Seidenberg theorem that says that every set in n+1 dimensional real space defined by polynomial equations and inequalities can be projected down to r to the n, 1 dimension less, such that the resulting set is still of this type. And why is this relevant? The important consequence is that the theory of real closed fields is decidable. So if you have a statement over the reals in this theory, you can decide it, and I will make this more precise in a minute. However, the proof, also it is constructive, led to an algorithm that is very impractical because of its high complexity. And it was a big breakthrough when cylindrical algebraic decomposition was invented by George Collins in 1975, that basically solved the same problem, but much more efficiently. And nowadays in computer algebra and in real algebraic geometry, this is a very fundamental algorithm. And yeah, in many other contexts, you can apply this algorithm. When I say it has a better complexity, this has to be taken with a caveat that the complexity is not really low. It's still doubly exponential, but it's so small that you can use it for some examples of interest. Of course, if examples get bigger, then also this algorithm becomes unfeasible, but for many interesting problems, it is feasible. Okay, so what am I talking about when I say the theory of real closed fields? So I give here a kind of grammar, what kind of formulas we can build. So we can use polynomials in an arbitrary but fixed finite number of variables with rational number coefficients. We can use relational symbols, less, greater, equal, not equal, and so on. We can use logical connectives and or negation, implication, and so on. And we can use quantifiers for all and exists. And all formulas that we can build from these rules are in this theory. So here are some examples. Here's a formula without quantifiers. So this is already a quantifier-free formula in 3 variables. Okay, we have 2 inequalities that are connected with a logical AND. And if you look, you see immediately see that, okay, the left one is a sphere in 3 space, and then you cut out some piece of the sphere. So this is what this formula says. Then here is another example of a formula. It doesn't have any particular meaning, just to show you the structure. For all x in R, there exists a y greater than 0, such that this inequality holds. And you see, this is a formula that does not have any free variable. Both variables are quantified. So at the end of the day, this statement is either true or false. And this algorithm can decide what is the case. And here is a kind of a mixed version. We have a quantifier, but also we have a free parameter a, and cylindrical algebraic decomposition can tell you for which choices of a this formula is true and for which it is false. Okay, so now let me explain why this is called cylindrical algebraic decomposition. First, we define what is an algebraic decomposition. So we say if we have given a set of polynomials, P1 to Pm, and we look at maximal cells that are sign invariant. So maximal cells, I mean connected sets, subsets of R to the n, in which all of these polynomials don't change their sign. They need not all have the same sign, but they are sign invariant in this cell, and I cannot make this cell bigger without violating this property. So this would be an example. So we have these 2 ellipses that are defined by these polynomial equations here. So these 2 polynomials. And so according to this definition, let me see whether you're still awake. How many cells do we get? 5. Yes, we get 5 cells. That was quick because I didn't say, but I wrote it here that when I say sign, a sign can be plus, minus, or 0. So we have 3 cells that are 2-dimensional, so the 2 fillings of the ellipses, the ambient thing here, and the 2 lines, 1-dimensional cells. Okay, so but this is not a cylindrical decomposition, because we say algebraic decomposition is called cylindrical if for any 2 cells their projection down by one dimension is either identical, is either the same set, or they are disjoint. So if you look here, and if we project down in this y direction on the x-axis, the two ellipses, we get two intervals that are definitely not the same, and they are not disjoint. Same with the orange thing. If we project it down, we get the whole real line, and this is not the same as the other projections. So this clearly violates this condition, and we can repair it if we add some vertical lines. You could think of, we add another polynomial that depends only on x and has exactly the zeros where these lines are. So now you see, if we look at any cell here, let's say this gray cell, and we project it down, and any other cell here, be it this line segment or this or another two-dimensional cell, they will be exactly the same interval. Okay, and there's a second condition. So if we do these projections of all the cells, well, we get a collection of sets in one dimension lower, and this collection of sets must recursively have the same property of being cylindrical. Okay, and then at some point you reach the base case. This is just a real line. Any algebraic decomposition of the real line is cylindrical by definition. So this is a collection of intervals and points that can be induced by a single univariate polynomial. Okay, so how many cells do we get now? Yeah, okay, it's boring. You can count. There are 13 cells that are two-dimensional, 20 cells that are lines or curves. Like you have to consider this as one, and this is another one, this is one, and so on. So you get 20 and 88 points, so we get 41. So how does a CAD formula look like? When we do this cylindrical decomposition, we get a formula that is equivalent to the input formula, and it has a very special structure. So let me first explain for a single variable. So if a single variable x, then a formula is said to be in CAD format if it's a disjunction of formulas phi 1 to phi m, where each one is a simple inequality like x less than alpha, or x between two values, x greater beta, or x equals some value. So it's a decomposition of the real line, not necessarily of the whole real line, but we have intervals and points, and they are not allowed to overlap. So then this is how such a formula looks like. And then by the recursive nature of the definition of cylindrical decomposition, we also get a recursive characterization of the structure of the formulas. So if we have now n variables, then a general form of a CAD formula looks like this. Again, we have a disjunction of certain things, and in each part we have a conjunction of two formulas, phi and psi, and so the phi's play the same role as above. So the phi's, they depend only on the first variable, and they are if I take them together, they are of the very same structure as the univariate case. And then the psi's are such that they are, so first of all, they are satisfiable formulas, so that can be made true, they are not contradictory, which are in now it comes the recursion in CAD format with respect to the remaining variables. Whenever, so they may also contain x1, whenever this x1 is replaced by an instance that satisfies the corresponding phi. Okay, so let me showcase a few simple applications, what you can do with CAD. For example, here's a problem, here's this rational function, and of course I said we have polynomials, but if you have rational functions you can simply rewrite as to have polynomials. This is not a big deal. So we want to know for which values of x this rational function is between 2 and 3. Well, and it's a one-liner you call, so this is, I use Mathematica, this is the mathematical notation, but if you prefer Maple, it will be very similar. So you call this command, you give the inequality, and you say what is the variable, and then instantaneously you get this result, which now, if you remember the form of the CID formula, matches a univariate CID formula. So we have 2 parts, and so here's the disjunction. We have 2 parts for the x, 2 intervals. Here's another example. So if a, b, c, and d are real numbers that satisfy ad minus bc equal 1, then the following inequality holds: a squared plus b squared, and so on. You can read it yourself. So now we have 4 variables. And again, we can just call cylindrical decomposition. This is our assumption. We write it as an implication. We say this condition implies this inequality, and our variables are a, b, c, d, and we get true. Get true. Because, so what happens internally, it computes this decomposition of r to the 4 into cells, and then since these cells are sign invariant regions, it suffices to check the statement that I want to prove on a single point in each cell. And so this is a finite number of points where this inequality is checked, and when it's true on each of these witness points, then I know it is true everywhere. And then the program returns true. Okay, a third example: if the sum of 4 positive numbers equals 4 times w, and the sum of their squares equals 8 times w squared, then none of the 4 numbers can be greater than 1 plus square root of 3 times w. Okay, how can we formulate this as a cylindrical decomposition problem? So let me first give names. A, B, C, D are these 4 positive numbers. And so we give here the condition that they are greater than 0, and without loss of generality, I assume that they are ordered in this way. Then we have here the 2 conditions on the numbers, on their squares, is this. And then I want to know for which W and A, for which combinations there exist B, C, and D, such that these formulas hold. And again, without much waiting, we get the answer. And so here you see now the recursive structure of a CID formula. So this is what was called the phi 1. This is on the first variable, a condition, W greater 0. And then here is a formula that depends on W, and whenever you instantiate in the second part W by some positive number, you get a CAD formula of 1 dimension less for A. Okay, so these are, let's say, toy examples. Now let me show you how, I have some exercises. So tomorrow we have an exercise session, so I will give some exercises that if you have time this evening, or you can try to solve, and otherwise I will just show how to do them. So here's another problem that can be proven in the same style as the ones before. We have this inequality. Okay, the new thing is that here's now an absolute value, but it's not too much trouble. And here's another one. If you look on the previous slide, example 2, the question is whether this bound is sharp. So example 2 was this one. So the inequality says that this expression is greater than 1, and the question is this 1 optimal, or can we improve it? And cylindrical algebraic decomposition can give you the answer. Okay. Okay, so this about the general introduction of the method. Now I would like to show how I use these tools in my daily work. So this is a joint work with Ali Unchu and Elaine Wong that is about unimodality of Gaussian polynomials. So this has relations to combinatorics. So we say a sequence of real numbers, a1 to an, is called increasing and decreasing, or strictly increasing, or de-strictly increasing if the consecutive differences are greater than or equal to d. This is obvious. And we say a sequence is called unimodal if there is some index m such that the sequence is, well, whatever. Yeah, okay, so for basic unimodality, we say if it's non-decreasing in the first entries up to m, and then it's non-increasing in the second half of the sequence, where this m need not be exactly in the middle, can be any index. And then we say strictly unimodal if all the inequalities are strict, or we say de-strictly unimodal if the differences are at least d. Okay, and so these are what is called the Gaussian polynomials, or maybe more known under the name Q-binomial coefficients. And this was an old topic to investigate these coefficients and show the unimodality behavior of the coefficients. So what is the Q-binomial coefficient? I suppose most of you know. I write it in this form with L plus M, choose M, and then it's the product of these factors. And if you expand it, you find that it's actually not a rational function, but it's a polynomial of degree L times M, and with certain integer coefficients. And so the result is that these integer coefficients, a classical result is that these integer coefficients form for any L and M a unimodal sequence. And so what we do is generalizations of this. So for example, Pak and Panova proved that this sequence from the Q-binomial coefficient is also strictly unimodal. However, this statement does not hold universally, but with some restrictions. So for example, they show that they restrict L and M to be greater to 5, and then there's still a few exceptional pairs that are only a finite list. So for example, if you look at the first case, 5, 6, or by symmetry is the same as 6, 5, we have this Q-binomial coefficient. If you expand it to a polynomial, you'll see this polynomial. And now if you look carefully, you find here 32, 32, 32. So this is not satisfying the strict unimodality property. However, so that this makes sense, one should make it a bit more relaxed, because if both indices L and M are odd, then we always have that the two middle coefficients are the same, so we do not, we are generous and don't look at this. Or, well, what we actually prove because of the symmetry, we say we prove the d-strict increasing behavior in a certain range. And then whether this implies unimodality or not is a matter of taste and definition. Okay, and so to do an algorithmic approach, we view this as an instance of a much more general class of problems. So the general setup would be the following. Let D be, so D stands for denominator, a univariate polynomial in Q with integer coefficients, and we assume, for reasons that will become clear later, that all of its zeros are roots of unity. And then the numerator n is a multivariate Laurent polynomial. So we have here in Q, and x is a set of variables, and we also have the inverses. So we have Laurent polynomials. And these variables x we will view as q to the something. So like in the q binomial coefficient, we had q to the L or q to the M in the definition. Okay, and then we define this sequence ck that depends on indices 1 to n, L1 to Ln, as the coefficient in the expansion of this rational function, the case coefficient in this expansion. So as an example, if we choose a single variable x and we view this as q to the L, and we define the numerator as this product and the denominator as this product, we end exactly with the q binomial coefficient as it was shown on the previous slide. And so then these coefficients ck are exactly what was called pk of L and M. So the q binomial coefficient fits into this setting. And so our general goal is that if we have certain inequalities that may restrict the validity where we want to prove the strictly increasing behavior. So this is our goal, that we want to prove that for a given d, that the sequence ck is d strictly increasing in a certain range. And the bounds of this range, the a and the b, they are allowed to depend on these extra variables. And so this is the general strategy. We first derive a closed form for this quantity ck. This is relatively easy and well known how this can be done. Then we can take the difference. We have to do some case distinction. I will explain this on concrete examples. And finally, we apply CAD to each case to show this inequality holds in the range of interest. Okay, so we start with the denominator. If we expand this rational function into a Taylor series, then we know, since we assume that the roots of the denominator are roots of unity, we get this exponential polynomial representation of the dk. So where we have these roots to the power k, and then depending on the multiplicity of this root, we have a polynomial in front. In case that we have several L's, we want to write everything, or if we have several roots of unity, we want to write everything in terms of a single root of unity. So we take the smallest L such that all of these roots are L's roots. And so now again back to our example, if we consider the q binomial coefficient L plus 3, choose 3, we have the denominator is well, these 3 factors. So we have as roots, we have 1, we have minus 1, and then we have here the third roots of unity. So we choose L equals 6, and we let omega be this primitive 6th root of unity, and then all the roots of this polynomial can be written in terms of omega with different powers. And so in the end, after a little computation that is not particularly difficult, we get this closed form. So you see that this matches here because the root 1, so omega to the 0, has the multiplicity 3. We get here a polynomial of degree 2, and then we get the rest. Okay, so this is not very surprising and not very deep. Now we have to include the numerator. So the numerator was some polynomial in q, and q to the L1, q to the L something. If we expand it, well, we get in expanded form some coefficients gamma I, and then q to the linear form in these L's plus something that I call here bi. And so this whole thing defines our coefficient ck. Now if we want to write these coefficients ck in terms of the dk, that were the coefficients of the expansion of the denominator, we can do this because, well, if you think here of this power series, you just have to pick the corresponding ones, and it's just that you have to subtract what is written here in the exponent. However, there's a little caveat, because these coefficients dk, just by definition, as they are coefficients of a power series expansion, they are of course 0 when the index is negative. But if we take this closed form, it's not guaranteed that this evaluates to 0 for any negative k. This thing here it does not give 0 for all negative numbers. And so this is a problem that must be cured. So this splits your function into regions of validity where you take only certain parts of this sum here. So you say if k, let's say, is from between 0 and L1, then I have to omit some parts of this sum where this index is negative, because I don't want to evaluate at negative indices the dk. And so what we get looks as follows. So let's get back to the example. We have this numerator. When we choose m equals 3 in expanded form, it has this form. Now we can immediately, because of the symmetry, we only look for k from 0 to 3 over 2L. So we can omit all these terms here because they are beyond the range that we are interested in. And then the first 4 terms translate into this representation for the pk. However, well, if we consider this, what I just said, we have to split this range into 2 pieces up to L, and then from L to 2L or 3 over 2L, whatever we like. Okay, yeah, and then it looks like this. Now we want to prove this monotonicity, so it's clear that we look at the difference of 2 consecutive items. We want to show that it's greater than D. The problem is we cannot yet apply CAD directly on this, because we have still these symbolic powers. So these things are not polynomials. But of course we can make them vanish, because since we know that they are roots of unity, so the L's power is 1, and we can eliminate all these roots of unity by doing a corresponding substitution. So we scale by L, and then we have to consider all possible remainders kappa or lambda I here. And depending on what the L is and the N is, we get a lot of case distinctions. So we get this many case distinctions. And now to each of these cases, now we can apply CAD. And well, I will show you one of these cases. You could argue, well, this is not particularly difficult, but if you have to do 100 of such cases, then maybe you don't want to do it by hand, but you're happy if you have a tool that just does it for you. So if we build a difference in our example, in the simple example, we get this expression. So here we still see the powers of the roots of unity. Now we had L equals 6, so we get 36 cases. And one of these cases, where I pick this one, now gives this representation. So everything simplifies a lot. All these omegas disappear. The conditions here also change, of course, now in terms of K prime and L prime. And okay, so assume we want to prove strict monotonicity. No D or D equal 1. Then, and the first line is kind of uninteresting because this is obviously positive, but the second line is not so obvious. So this translates into the following formula. So we have first the assumptions that K prime and L prime are both non-negative. And then here we have this condition. And we want to prove that this implies that this guy here is at least 1, because we want to prove strict monotonicity. So we apply CAD to this formula. and we wish to get true, but we don't get true. We get something that looks very complicated. And here you can again match what I told you about this general structure of a CAD formula. So we have here, the first part is always a condition on L. Here's a condition on L, and what follows then says something about the K. But now if we read this carefully, we see, well, the first clause says basically is a single case L prime equals 0. Same for the third clause here. We have that L prime is an integer and the only choice is L prime equal 1. So because we have to consider that CAD doesn't know integers, it works inherently over the real. So whenever we call CAD, we assume that all the variables are real variables. Well, the second clause, this condition here can never be satisfied for any integer, so this is not interesting. The only interesting is the last line here. So when L prime is greater than 1. And now it says that, well, the negation of this tells us the formula is false under this condition. So this allows us to extract some exceptions, because there must be some, otherwise this formula would not be like this. Yeah, okay, if you investigate this, you get an infinite family of places where this is violated. And this tells us that the q-binomial coefficient with m equals 3 is not a strictly increasing sequence in general, and in particular not because in these places the strictly increasing behavior is violated. And of course this is not a contradiction to the theorem of Pak and Panova, because they had started for L and M greater than 5, greater than or equal to 5. Okay, and then, so the nice thing is that all this works automatically, so you can do a lot of cases without having to work too much. And so this is one of the theorems that we proved. So for different choices of D is the D-strict thing, and different choices of L and M, so M in this range, L, and general L, we prove that this D-strict increasing behavior is indeed the case, and we identify precisely what are the bounds where it holds, what are the exceptions, and it's tedious to look at these numbers, just that they are there, up to D equal 5 strict behavior. And I don't see any elegant way how to prove such things without these tools. Okay, this was the first application. And there's another one. That is joint work, again with Elaine Wong, my former PhD student, on monochromatic Schur triples. Also in this context, we used CAD. And so what is a Schur triple? A Schur triple is a triple x, y, z of integers that satisfy x plus y equals z. Very simple object. And so if we consider a 2 coloring of the natural numbers from 1 to n, so for example we can say 2 and 4 are red and the other ones are blue, then we can talk, here's a graphical representation of this coloring. Then we can talk about monochromatic Schur triples. So triples of numbers that satisfy this condition and where all the numbers have the same color. So for this coloring here, we get 3 such monochromatic Schur triples. And in this context, the interesting question is, what is the minimal number of monochromatic Schur triples that I can achieve in a range n when I'm free to choose the coloring? So you fix n, you reason over all possible 2 colorings of this range, you compute the number of monochromatic Schur triples and you take the minimum. So for example, was this number 4, was this the minimal number we can get for n equals 6? Who knows? So what is the minimal number for 6? And what is the coloring that yields this number? And the answer is, if we choose this coloring, then there's actually just a single monochromatic Schur triple, that is the triple 1, 1, 2, and there does not exist any other monochromatic Schur triple. So this minimal number M6 is equal to 1.
And this also contradicts a potential conjecture that one says that the ones realizing the minimum size k are the string that is k plus 1, for example, because 1, 2 wouldn't be good for size 2.
Yeah, yeah.
So you really have to restart at n plus 1.
Yeah. Right, yeah. So this doesn't give you any information for the next one. Yeah. Okay, and there was, of course, a lot of work already on this problem by Robertson, Zeilberger, Schön, and many other people. And so in particular, they showed that for so this number is minimized when the coloring has a very particular form, namely you have a run of red numbers, then a run of blue numbers, and again a run of red numbers, similar to the example what we have seen. And you can identify where, how long each of the segments is, has to be approximately, such that this minimum is achieved. And so it's not difficult to work out a formula that given, so S and T characterize the length of these runs. And so that gives the number of the number of monochromatic Schur triples of length n in terms of S and T as a concrete formula. And then you can do some simple exercise in multivariate calculus to derive these numbers 4/11 and 10/11. However, this is not the complete answer because, well, what do you do when n is such that these numbers are not an integer? Then you somehow have to round, and a priori it's not clear whether you should always round to the nearest integer or if there are some exceptional cases. So what is the exact formula? So here's the situation. For n equal 33, we don't have this problem because 33 is divisible by 11. And so here on this picture, you have the axis, you have the y, and then these diagonal lines indicate that, well, when you take two elements from this set and they are below this, then it's a Schur triple. Or you can make a Schur triple out of it. So if these are red, then you get this triangle of monochromatic Schur triples. So every dot in these colored triangles corresponds to one monochromatic Schur triple. Like this point here is the first point here in the corner is the triple 1, 1, and then the third entry is 2, of course. Yeah, okay, and here we get 87. And so here's the precise formula, how you get the numbers that really minimize it when you use the floor function. And you see that here you have to add this plus 2 to get the 2 minimum. And how can we prove this? Well, we prove this by case distinction, mod 11. And then so that the floor can be resolved easily. And then we get a expression of the form. So let's say, so we claim that these are the points where the minimum is achieved, S0 and T0. And we want to show that whenever we change this, then the number doesn't get smaller. So we want to show that this expression is minimal for I equal j equals 0. And this is, of course, something now that you can again apply cylindrical algebraic decomposition to prove it. And again, there's a caveat because here, of course, I and j are integers, but CAD doesn't see that. It treats I and j like real numbers. And so this is one instance how this can look like. So we get here such a polynomial. Okay, we want to show that this is minimal. So this amounts to showing that this polynomial, that this part here, is non-negative. And if we feed this into CAD, we get the following. So we copy this polynomial, we ask, yes, we decompose this polynomial, yeah, and maybe we should say here greater equal to 0. It does not yield true because this polynomial is not positive everywhere or non-negative everywhere, but there is this ellipse, and inside the ellipse it is negative, and outside the ellipse it is positive. And we are just lucky that there is no other integer point inside the ellipse. Okay, so, and yeah?
The solution is not unique. There are 3 solutions.
Exactly, here there are 3 solutions, yes, that give the same number. So that makes our job to find a nice formula easier because we have some freedom and we don't have to present the formula by case distinction, which we have to do in other situations. And so still now what do? We don't want to investigate this by hand. So first of all, we can check all points that are close to here. This is just a finite number. Let's say all points here in this square, we can just check. And then we prove by cylindrical algebraic decomposition the formula that assuming that I and j are outside of this square is then the polynomial non-negative. And then this can be achieved, and yeah, we don't have to work by hand. So, yeah, then this is the theorem that comes out. So you get a nice formula, and you have, for the proof, you have to make a case distinction, as I explained. And then we since now we had the implementation and this algorithm, we can apply it to different situations. So now we can generalize Schur triples to not just x plus y equals z, but we can have some factor in front of y. So this corresponds to pictures where these lines are not exactly diagonals, but have some other angle. And then, for example, we get a theorem like this. So the minimal number of monochromatic generalized Schur triples, now here we have the 4, that can be attained under any 2 coloring of this form, is given by, again, an expression. And now this is what I meant. Now here we have to make this case distinction. So here we were not able, even with playing with this non-uniqueness, to find a nice formula, but here you have to explicitly state a certain set of exceptional indices. And you see here we have to make 108 case distinctions, and of course this is something that you don't want to do by hand.
But the theorem that was telling that the optimal one was of the form f to the power b to the power f to the power, is easy to generalize in this case?
Which one?
Well,
here?
The starting point was a theorem of the 19th.
Ah, you mean the Zeilberger thing?
Yeah. You don't have it when you have A.
Here?
Exactly. If you don't have the starting point, the search ground would be all the binomial.
Oh, yeah, right. So this is, so for this situation, they could really show that this is that the minimal one is achieved for such a coloring, and this is not anymore true for when we change the A. Yes, not necessarily. So for some A, we have found colorings that are not of this form that give lower. That's why in the theorem we restrict and say under the assumption that the coloring looks like this, then you get this number. And we don't claim that this is the absolute minimum that can be achieved.
But they are still a bit similar with more rounds, or they are completely fancy?
Well, I mean, I don't know what is the true. It can be, at least for the fractional a, we have observed that it can be very complicated, and we don't have any clue for general n what the coloring has to look like.
Okay, so it's widely open.
Yeah, sure. Okay. Yes, this was all I wanted to say about the Schur triple thing. And then there's a third application of cylindrical algebraic decomposition that is called the Gerhold-Kauers method, named after Manuel Kauers and Stefan Gerhold, two former colleagues from RISC. That is a method for proving inequalities that are not anymore polynomials, but that also involve sequences that are defined by recurrences. So as an example, look at this inequality. So the Fibonacci polynomials are similarly defined as the Fibonacci numbers, just with this extra parameter x. And then it's an inequality that says this polynomial squared is less than this expression. And well, neither is this a polynomial, also it's called Fibonacci polynomial, but now as it's written like this, it's a symbol. It's not a concrete polynomial. And also here we have this exponent, so it's not a formula that you can feed into cylindrical algebraic decomposition. And so their idea of how such formulas can be proven is to set up an induction with respect to n. Then you replace all non-polynomial expressions by new variables, and then you can try to prove the resulting formula by CAD. So here's a sketch of the algorithm. Let f of n denote the whole formula. So let's say we bring everything on one side of the inequality. Then the goal is to prove that fn is greater than or equal to 0. And this formula, this function, this rational function, say, can now involve n, this is the index, and several sequences, and there can be extra parameters x. And there can be some constraints, let's say x positive or whatever, and we give a bound n0 of how far the algorithm should try. And so the goal is to prove that this formula is non-negative for all n in the natural numbers and under this given constraints C. So the algorithm builds an inductive scheme. So we start with an induction of length 1. So we set m equals 0. That says as an induction base, we have to check the case m equals 0. So we check the formula when we substitute n by 0. This is the induction base. And now we set up a formula that says assuming fn greater than or equal to 0, fn plus 1, and so on, up to fn plus m, then this implies that the next one is also greater than 0. So it's an induction of length m, using the last m plus 1 values as assumption to prove that the next one is also satisfying this condition. So now we have to do two steps. The first step is to rewrite all these symbols f, these sequences, in a minimal possible way by unrolling the recurrences. They're defining recurrences. And second, each of these symbols that is surviving is replaced by a new variable. And these are the variables that CAD will work on. Then we can apply CAD to the resulting formula. Of course, again, it will assume that all the variables will be real, which sometimes, of course, can be a problem. And if this returns true, then we have a proof, because we have checked sufficiently many induction base, and we have done the induction step. And we do this as long as our induction depth is not n0, otherwise we stop and say fail. So here's maybe the most simple example where this method applies to is Bernoulli's inequality, is very well known. 1 plus nx is less than x plus 1 to the power n, under the constraints that x is greater or equal to minus 1. So our sequence is given by this expression. So this is the part that does not fit into this polynomial setting. Then what I called capital F on the previous slide is just then this y minus nx minus 1. And the constraint is given here, and also n greater than or equal to 1. So we start with m equals 0. We check the induction base. This is simple. And then we write down the following formula. We give here these constraints. We also assume that the inequality holds for n. And we want to show that this implies it holds for n plus 1. So a very classical, simple induction proof. Now we use the recurrence. We have here this x plus 1 to the n plus 1. We write this as x plus 1 times the original f. And then we substitute fnx by y. So then this formula looks as follows. So here this becomes a y. And this becomes x plus 1 times y. And now you see what is written here is a perfect Tarski formula that you can feed into CAD. No obstruction, and if you call it, it yields true. So that in this example, we immediately get the proof. If this was not the case, then we could try a higher induction scheme until we run out of time or memory. Okay, if you want to try this method, you can try to prove this inequality on Fibonacci polynomials. And this brings me to the second topic, which is shorter than the first one. So let me see how far I can get in less than 20 minutes. So this is about guessing and applications of guessing to a set of problems that was inspired by a puzzle. So here you see a puzzle. It's a chessboard, and you can put black and white dots on each place by following these rules. So you put black and white circles. Each row and column must contain equally as many white circles as black circles. And no individual circle may be sandwiched horizontally or vertically by circles of the opposite color. So if you feel bored, you can try to solve this puzzle while I'm continuing to talk. Also, I have to disappoint you that this one is a very simple one, so you will figure it out in a very short time. Actually, but what we are not interested in is solving these puzzles, but seeing these puzzles as combinatorialists, you have already certain counting problems in mind. So if we don't fix the dimensions of this grid, we can ask, first of all, how many such binary matrices are there without any restrictions? This is, of course, a very boring question, very simple answer. And so here we have two conditions, so we can look at what happens if we impose only one. So let's say, how many such matrices are if we only use the first rule, that each row and each column must have the same number of circles of each color. This gives an interesting counting problem. We can forget about this balancing. We can ask how many such matrices are that do not have this sandwich property, or generally speaking, that have a certain pattern avoidance. And then we can ask how many matrices are that have the balancing condition plus the pattern avoidance. Okay, this is what I just said. I just wanted to keep the puzzle on the screen for a while. And so first, I want to focus on this case where we impose the balancing condition. And for this to work, of course, we have to assume that the dimensions are even numbers. And so let me denote by bk of n the number of balanced matrices of dimension 2k times 2n. And so from now on, we will assume that the k is fixed given integer, and then view this as a sequence in n. Yeah, and so this is this famous quote by Polya: first guess, then proof. This was also my guiding principle when I designed this talk, because I was thinking, should I first talk about creative telescoping and then have this chapter about guessing, or the other way around? There are reasons for both choices. And then Polya told me, first guess, then proof. And so here, as an exercise, if you like, you can try to compute as many terms as you can for B3. So this is the number of balanced 6 times 2n binary matrices, or the next case is B4. And of course, I ask you not to cheat, because we have already computed the recurrences and they are already published. And of course, if you just use the recurrence, you can compute infinitely many values, but let's say from scratch. So I tried to do it, and I don't know if I did it particularly clever. Maybe some of you have a better idea and get more numbers than I was able to compute. I would like to see that. So when we do this for B3, we can use the numbers to guess a recurrence equation. And so it looks like that these numbers satisfy this recurrence. And if you want to see that this is not just a guess, but a theorem, then you have to wait until tomorrow.
How much time do you need to compute?
So it's for B, I can tell you for B4, using a lot of time and all the computing resources that we had, I was able to compute 150 terms. That was several days of parallel computing on a very big machine. And for this, it's much easier. So this, I don't remember precisely how many you need for this, but you can see that order is 4, and the degree is something like, 6, 8. So you need something like 40 terms maybe.
So they must just be balanced horizontally and vertically.
Yeah. So of course, you know how to do this in principle. Right?
Yeah, because you can.
Yeah.
You can permutate the columns as you want, so you can count all the type of columns.
Sure.
Then you use.
Yeah, I will. I mean, I guess you know, of course, how this works. I will explain it tomorrow as well. But tomorrow is about the proving. Today is.
We use the computers so heavily then.
Okay, you can try. We will see. Okay. I didn't find it that easy. But as I said, I'm happy to be taught a method that makes it faster. Yes. Okay, so naive guessing. Well, I guess all you know. You can, when you have given the first capital N number of terms of the sequence, you can just set up a linear system. And so what you first need is some kind of idea what kind of recurrence you look like, and in German we call this an Ansatz. And since there seems to be no equivalent word in English or French maybe also, that's why we use this word in English. So let's say we assume that there's a linear recurrence of order R with constant coefficients. Well, then we instantiate this sequence with different values of n. So if we choose n equals 0, then we insert the numbers a0 to ar. When we choose n equal 1, we get the second row of this matrix, and we try to find a solution. If we have polynomial coefficients, let's say if we have linear polynomials, then we get a matrix that looks more complicated. We get more columns corresponding to these additional unknowns that we have. And in general, we look for a recurrence of order R and of degree D, and then we get a matrix that has this shape. So we have this many unknowns in the ansatz, R plus 1 times D plus 1. And if we assume that we have given the first n values, so from A0 to AN, then we get, by writing down this matrix, we get n minus R plus 1 equations. Of course, if you write down a random matrix with fewer rows than columns and you compute the null space, you will always get something. And this is then usually absolutely meaningless. So when you do this kind of ansatz, you want to have a matrix which has at least as many rows as columns, so that the occurrence of a non-trivial null space is really something meaningful and something unexpected. And this gives you trust in the result. So if you have solved the other exercise, or if you are not want to compute these numbers, you can look them up. This is the sequence number for B3. You can try to guess this recurrence that I showed on the previous slide with naive guessing, or with the next version of guessing that is not as naive that I show on the next slide. This is called order degree trading. So it's clear that since we have r plus 1 times d plus 1, we can, and we want to be below the number n, when we have given a certain number of terms, let's say we have given 33 terms, then all the points that are below this curve can be chosen for r and d. And terms above the curve give something where the matrix will be of a rectangular shape not in our favor. And if we get more terms, well, then this curve increases and we can have bigger recurrences that we can find with this number of terms. And then typically what happens for a recurrence, there's not just a single recurrence, but you can find higher order recurrences also that are somehow, if you think of operators, multiples of the recurrence, or consequences of the minimal recurrence. You think of the minimal recurrence, you shift it by 1, you add the minimal recurrence, you get another recurrence of 1 order higher, and this is of course still valid. And they have this, they also have such a curve. So this red curve says for everywhere where this hits an integer point, there exists a recurrence of this data. Let's say here with r equal whatever 8 and d equal 10. Yeah, it would be this, and so on. And we see, so typically we want to have the one with the minimal order, so that corresponds to how far this curve goes here. And you see that, let's say, assuming this is hitting this dot here, that here you need more terms. Here you lie above this curve, but if you guess a recurrence of this data, you are below the curve. You can find this. You cannot find this directly, but you can find this one. And then what you do is you don't hit for the minimal order one, but for such a recurrence that has a higher order but a much smaller degree, and therefore can be found with fewer terms. And then there is a way to construct the minimal order one from this one. I mean, very naively, you could use this recurrence to compute more values and then do a guessing again, but more clever is to use GCD computations on operators that I'm not going to explain now, maybe tomorrow. And so what we were asking is, can we do other tricks to find recurrences from fewer values? So we call this guessing with little data. And so this refers to the situation where we have too little data, so that n minus r plus 1, this is the number of rows of our matrix, is less than the number of columns. Then we for sure will get a kernel that has dimension greater than 1. In most cases we just get rubbish. So most elements in this kernel are not meaningful at all. But maybe there is one single element in this space that is the true recurrence that we are looking for. But it's, of course, very difficult to identify this particular recurrence. So in some sense, we have a big haystack, and we are looking for a small needle in this haystack. And the question is, how do we do this search? So when I was working on this question with Manuel Kaus, we thought of what criteria could we apply to filter this set. Well, a good way of trusting a guessed recurrence, at least if you start with an integer sequence and you know that the sequence has integer values, is that you take the known values and then you use the recurrence to compute more values. If this is an artifact recurrence, most probably you will get rational numbers. If that recurrence that you guess produces integer values, this is a very strong sign that it may be meaningful and correct. Or another criteria could be that you look at the corresponding generating function and you investigate the differential equation, and then you know that for sequences that have a combinatorial origin, these differential equations are particularly nice, have a very nice singularity structure. Or there is something called the p-curvature that you can use to test whether this is a very special operator and so on. But the problem is all these conditions lead to very bad criteria, nonlinear equations and sometimes Diophantine equations that we don't know how to solve efficiently. So there we have no way of checking these, for incorporating these conditions in the search. Of course, when you have given a concrete recurrence, you can test this, but not at the stage when you make your ansatz.
So, I don't even understand what does this mean. So when the dimension of the kernel is bigger,
yes,
you're not filtering a list, you are filtering a linear space.
Right. That's why it's a haystack. We are not looking for a finite list and try to pick one element from a finite list, but we want to find one element in an infinite set. This is the point, yeah, and that's why, and so if you try to use these filters, you get very ugly equations that you would have to solve, and we cannot do this.
So these Diophantine equations, they are in the coefficients
yes.
of the recursion?
Yes. Yes.
So in fact, only the second filtering criterion seems clear to me. Maybe every generator has some non-regular singularities, and you have to cancel them out one with the other. Unrolling the recurrence. Think of the recurrence being written down with generic coefficients. Of course, you can write down a formula what this recurrence would produce for the next value in terms of all these coefficients. But you see, this gives a nonlinear equation. And the only thing that we came up with that gives something reasonable is that we assume the coefficients of the recurrence involve relatively small integers. Because this is what we observed for long in practice, that once you do your guessing and you find some artifact recurrences, they usually have huge integer coefficients. Much bigger than the coefficients of the small, of the true recurrence. And so this led us to call on another tool of computer algebra, that is the LLL algorithm, the lattice reduction algorithm. And I think this is a very good cliffhanger to stop my talk now, because now you want to know what this algorithm does and how it solves this problem, and I will explain this to you tomorrow.